All right, we are looking at notes Y, where we're going to solve exponential and logarithmic equations. We got 2 and 3 hanging out. Hey, do you guys want to meet my new friend? Sure, but where is he? He's right here. Poor 8. Why can't anyone else see you? Square root of negative 1 beats me. Remember that square root of negative 1 is I. So we got an imaginary friend going on. I think a lot of us might have imaginary friends right now with all this social distancing. All right, so like I mentioned, we're looking at notes Y. This is module 12 now, and we're solving exponential and logarithmic equations. We're going to look at solving exponential equations first, and then we're going to switch gears over to logarithmic equations. All right, there are 2 types of exponential equations. The first one is an equation that can be written in the form b to the f of x equals b to the g of x. So let's write this out. Equation can be written in the form b to the f of x equals b to the g of x. So notice that they have the same base there. Okay. If that's true, then because the bases are the same, we know that their exponents are the same. So f of x equals g of x. All right, our second form is if we can't write both sides using the same base, then we are going to have to use some natural logs. So if you can't write both sides using the same base, then use the fact that the natural log of a to the f of x equals the natural log of b to the g of x. Sorry, I started writing f there. Okay. And we're going to be able to bring down the exponent and solve. So notice that in this setup, we had a to the f of x and b to the g of x. They have different bases. So because they have different bases, essentially I have to take the natural log of both sides. So I have 2 scenarios. My first one is they have the same base. And if they have the same base, I can simply set their exponents equal to each other. If they don't have the same base, then I am going to take the natural log of both sides, and then I'm going to bring down those exponents to the front, and I am going to solve my equation from there. Okay? Every exponential equation we come across is going to come in one of these 2 forms. So as we go through our examples now, we're looking to see which version we have. Okay. Our first example is 2 to the x equals 32. Here's my thought process. On the left-hand side, I see that there is a base of 2. So I'm going to ask myself, is there any way that I can write 32 with a base of 2? And there actually is. 32 is 2 to the 5th. So this would be the same as 2 to the x equals 2 to the 5th. Now that they have the same base, I just set their exponents equal to each other, and I get that x equals 5. Now, in the next example, I have 4 to the x equals 24. The base on the left-hand side is 4. So I'm asking myself, is there any way I can do 4 to some exponent that would equal 24? It's not going to work because 4 squared would be 16, and then 4 cubed gets me to 64, so it jumps right over that 24. There's no way I can write 4 or 24 with a base of 4. So because I can't make them the same base, I need to take the natural log of both sides. So I'm going to take the natural log of 4 to the x equals the natural log of 24. Now, we are going to bring our exponent down front. Notice that that right-hand side doesn't have an exponent, so we just don't worry about it. And we are left with x ln of 4 to the x. Nope, just kidding. We brought down that x to the front. So we have x ln of 4 equals the natural log of 24. Now, keep in mind, we're solving an equation. We are trying to get that x by itself. Right now, the x is connected to the natural log of 4 by multiplication. To undo multiplication, I use division. So I'm going to divide both sides by the natural log of 4. And we get that x equals the natural log of 24 over the natural log of 4. This is my final answer. You might be tempted to try to reduce 24 over 4. Can't do it. There's no logarithmic property that tells me when I have two separate logarithms being divided that I can do anything with it. Leave it just like it is. It's two separate logarithms, one in the numerator and one in the denominator. Now, this answer, though, is what we would consider our exact answer. Sometimes they might ask you for an approximate answer or an answer rounded to a certain number of decimal places. So, for example, if I wanted the answer to 4 decimal places, I would have to put into my calculator the natural log of 24 divided by the natural log of 4, and I would get that x is approximately 2.2925. That 8's going to round that 4 up to a 5 in that 4th decimal place. So this is my approximate answer. So right here in this slide, you have an example of each type of equation. You have the first one where we can make the bases the same. So we just set their exponents equal to each other. The second one where we cannot make their bases the same. So we take the natural log of both sides and bring down that exponent. All right, here's our next example. We have 5 to the 2x equals 125. My base is 5. So I'm asking myself, can I do 5 to something to get 125? Can I make those bases the same? I can. 5 cubed is 125. So I'm going to rewrite this as 5 to the 2x equals 5 cubed. Because they have the same base, I'm able to set their exponents equal to each other, so I get 2x equals 3. Now on this one, I've got to go one more step because I want to get that x by itself. I need to divide by 2, and I get that x equals 3/2. This next example, 4 to the x minus 5 equals 4 to the 3x minus 4, we already have the same base. Left side and right side both have a base of 4, so we're going to be able to go straight to setting those exponents equal to each other. So we get x minus 5 equals 3x minus 4. And now we just got a good old linear equation to solve. So let's get our x's over to the left. We're going to subtract that 3x. We get a negative 2x minus 5 equals negative 4. Let's bring that 5 over to the right by adding it. We get negative 2x equals 1. And that last step is to divide by negative 2. And we are left with x equals a negative 1/2. There we go. Not so bad, right? Okay, next up we have 5e to the x equals 10. My base here is e, but realize that before I do anything on this problem, I want to get the base to the exponent isolated first. I've got that 5 hanging out in front still, okay? So very first thing we need to do is we need to get the base to the exponent isolated. And we want to do that first. So we are looking to get that e to the x isolated. We want to get that by itself. In order to do that, we're going to have to divide both sides by 5. And we get that e to the x equals 2. I now have that base to my exponent isolated on that left-hand side. My base is e. So I have to ask myself, is there any way that I can make 2 be equivalent to e to the something? Not that I know of off the top of my head. So if I cannot make my bases the same, I need to take the natural log of both sides. So we're going to have the ln of e to the x equals the ln of 2. Bring that exponent down to the front. Whee! And we get x ln of e equals the ln of 2. Anybody remember what the ln of e is? It's 1. So this is really like x times 1 equals the ln of 2. But x times 1 is just x. So we get x equals the natural log of 2. So if that little property there escaped your mind, make yourself a little note. The ln of e equals 1. That's a good one to know. It sneaks up on you. Now, again, this is my exact answer. They might also ask me for an approximate answer. So if I were asked for an approximate answer, let's go to 4 decimal places again. I would need to, in my calculator, type the ln of 2. And I find that x is approximately 0.6931. There we go. All right, next up I have 1/5 to the x plus 4 equals 5 to the 3x plus 10. So on my left-hand side, I have a base of 1/5. On the right-hand side, I have a base of 5. We want to make these bases the same, and we can definitely do this, okay? Easiest thing to do, in my opinion, is change that base of 1/5 to a base of 5. The way we need to do that, though, is by using the reciprocal. Remember that to get the reciprocal, I need to add a -1 to my exponent. That negative exponent gives me my reciprocal. So this would be the same as 5 to the -1 times x plus 4 equals 5 to the 3x plus 10. I have the same base now, so that tells me I can go straight ahead to putting those exponents equal to each other. All right, over on that left-hand side, this is really negative x minus 4 equals 3x plus 10. Let's move that 3x over to the left. We get a negative 4x minus 4 equals 10. We're going to move that 4 over to the right. We get negative 4x equals 14. And my last step here is going to be divide by -4. So I have that x equals 14 over -4. We can reduce that. This would give me a -7 over 2. Now keep in mind with fractions like this, I can put my negative in the denominator, the numerator, or in the front, any one of those three places, and they will be equivalent to each other. Lots and lots of examples in this section, which is good for practice. This time we have 7 to the 2x minus 3 equals 32. I see a base of 7. I cannot come up with a way to write 32 with a base of 7. Just can't do it. So, if I can't make them have the same base, what do? I take the natural log of both sides. So I'm going to have the ln of 7 to the 2x minus 3 equals the ln of 32. Okay, I need to bring my exponent down front now. Now be super careful here because 2x minus 3 is in my exponent. It needs to stay together. So when I bring it down front, I got to make sure it's in parentheses. Times the ln of 7 equals the ln of 32. Now, at this point, I personally would notice that the 2x minus 3 is connected to the ln of 7 by multiplication. We can undo multiplication how? You got it, using division. So let's divide both sides by the ln of 7. This would give me 2x minus 3 equals the ln of 32 over the ln of 7. Let's add that 3 to the other side. And we're going to get that 2x equals the ln of 32 over the ln of 7 plus 3. Okay, now we need to divide by 2. Almost wrote a -2 there. And I have to divide that entire right side by 2. I can either write one big fraction bar divided by 2, or I also could do this in 2 pieces. This is going to be x equals the ln of 32 over, watch how I write this, 2 ln of 7 plus 3 over 2. So that 2 belongs in both denominators. We got to give it to both pieces. There's my answer. Now, looking back here at this step where I had 2x minus 3 times ln of 7 equals the ln of 32. The other option would be that I can actually distribute that ln of 7. If I did this, I would get 2x ln of 7 minus 3 ln of 7 equals the ln of 32. I would add the 3 ln of 7 to the other side. And I would get 2x ln of 7 equals the ln of 32 plus 3 ln of 7. Now, at this point, I'm trying to get that x by itself, so I'm actually going to divide by 2 ln of 7. Okay, and that's going to leave me with x equals the ln of 32 plus 3 ln of 7 over 2 ln of 7. Now think about this, that 2 ln of 7 belongs to both pieces in the numerator. If I were to break this apart, it would simplify to the same answer I just got. Ln of 32 over 2 ln of 7. And in that second piece, my ln of 7s would actually reduce and I'd get 3 over 2. So either way, we're going to get that same solution. So you've got a little bit of options there depending on which one jives better for you. Keep in mind, this is my exact answer. If I want an approximate answer, just make sure you're reading your directions. I'd plug that into my calculator and round to the appropriate number of decimal places. All right, we've got one last example before we do an application problem. This one says 7 to the x over 6 equals 3. My base is 7. Is there any way that I can rewrite 3 with a base of 7? Nope, can't do it. So I need to take the natural log of both sides. Bring down that exponent. And I'm going to get x over 6, ln of 7 equals the ln of 3. Okay, how is that x over 6 connected to my ln of 7? Multiplication. How do I undo multiplication? Division. So I'm going to end up with x over 6 equals the ln of 3 over the ln of 7. My x divided by 6, I undo division with multiplication. So I am going to get that x equals, I'm going to write that 6 in the front. 6 ln of 3 over the ln of 7. There we go. This is my exact answer. If I want an approximate answer, I've got to enter that into my calculator. I'm going to go to 4 decimal places again. I would get 3.3875. Awesome. Hopefully you're seeing the patterns, you're getting the hang of it. Okay, now, we previously looked at an application problem and I kind of left you guys hanging and I said, oh, you can't do it yet. Okay? Let's see one. It's not the exact same one, but it's similar where we're going to be able to solve it now. It says a computer purchased for $1,300 loses 20% of its value every year. The computer's value can be modeled by the function v of t equals a times b to the t, where v is the dollar value and t is the number of years since purchase. Give the function that models the decrease in value of the computer. So it tells me 2 different places that we're losing value. It says it loses 20%. The value is decreasing. So if we are losing 20%, it retains 80%. And remember, we get that 80% by doing 100 minus 20. Okay, and remember that in these types of problems, I have to write all my percentages as decimals. So, my equation is going to be the following. I'm going to have v of t equals that initial amount was $1,300, and it retained 80% of its value. We're going to write that as a decimal, so it's going to be 0.80, and we are using t years right now. It doesn't tell us a number of years just yet. So this would be the equation that models the value of the computer. Now, it says, in how many years will the computer be worth half its original value? Round to 1 decimal place. So, if it was purchased at $1,300, half of that is going to be $650. So we want to set this value equal to 650. So we get 650 equals 1,300 times 0.80 to the t. Now remember that when I solve an exponential equation, I want to make sure that I get my base to the variable isolated. Okay? And if it makes you feel any better or more comfortable in terms of the way that we've seen these equations written so far, you can write that 650 on the right-hand side as well. But remember, I'm trying to get this base to my variable, to the exponential variable, isolated first. So I actually have to divide by 1,300 to begin with. And I'm going to have that 0.80 to the t equals 1/2. Now, is there a way that I can easily make both of these sides of my equation have a base of 0.80? Not easily. Okay, so if I can't make my bases the same, I am going to take the natural log of both sides. So I get the natural log of 0.80 to the t equals the natural log of 1/2. We could also write 1/2 as 0.5 if you wanted to. Bring down that exponent. Whee! And I get t equals the natural log of 0.80. I just made up that equal sign. Go back for me. Beep, 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 beep. I get t times the natural log of 0.80 equals the ln of 1/2. T times the natural log of 0.80, undo that multiplication with division. We're going to divide both sides by the ln of 0.80. And we are going to find that t is going to equal the natural log of 1/2 over the natural log of 0.80. It specifically tells me in this problem to round to 1 decimal place. So I know I have to go ahead and put that expression into my calculator. And I'm going to get that t is approximately 3.1, use those units, years. So after about 3.1 years, that computer is going to be half its original value. All right, we're going to end this video here because next up is going to be my 2 types of logarithmic equations.